the next speaker is Jonas Schaible. He's a PhD candidate of the Hybrids grad school at the Helmholtz Center for Materials and Energy and the Zuse Institute in Berlin. And today we'll talk about his research on inverse designs of thin films using masked language diffusion models. Really looking forward.
Thanks for the introduction. Hi, I'm Jonas, and I want to talk about OptoLlama, which is a model which tries to address the inverse design of optical multilayer thin films by using discrete sequence generation models and specifically masked diffusion model. I want to start with this nice picture of a solar power plant on the top of the St. Pauli football stadium. And as you can see, it's not a generic solar power plant, but it has nice colors. And that's just like a way to, it was done using morphocolor technology, which is a thin film technology, which I want to address here, like similar problems. I start with the inverse design formulation of the problem in the beginning, then quick detour to diffusion models in general, then the masked diffusion models, which are also used in OptoLlama. Then I will want to show the performance of OptoLlama as well. So to start with, the problem of thin film inverse design. So first, the forward problem, we have some sort of material stack, so a layers of materials with certain thicknesses. You can simulate them or fabricate them and measure them and get out a spectrum. Here we have 3 channels: reflectance, absorptance, and transmittance. And then you compare and change the stack according what you got. When you now want to address this in the inverse design way is you first define your desired spectra, and then with a model or also with optimization, you obtain your thin film layer stacks. The challenge has, so this topic has some challenges. One is that there are many combinations possible of materials and ordering of the materials, and we are looking at about 20 layers of 20 different materials with about 50 different thicknesses. So the combinatorial space is quite large. But also there's the issue of non-uniqueness. You can have many thin film layer stacks which create a similar or the same spectrum. So to solve this, we use a diffusion model. So in general, I think you know all about diffusion models, but you try to map some sort of complicated unknown data distribution and map it to a known distribution like Gaussian noise. And between those points, you can define these two processes, the destructive process Q and the reconstruction P. And we try to use a machine learning model for P. We have these intermediate steps, But now when we look at discrete issues like our simulation, our inverse topic, there are some differences. So we have a token space where there are material keys and thicknesses concatenated together as one token. We have about 2,000 of these for all combinations of materials and possible thicknesses. Instead of the normal noising process, we use the remasking process. So in the beginning you have your sequence, and then according to a schedule, there's a probability to flip a mask to flip a token to a mask token. So the benefit of using this method is that it can address the complete sequence at once. It's not autoregressive. It can address the whole sequence and also reconstruct it in the end. So why OptoLlama? to represent the inverse design in this way, you can use can use mass diffusion, which has been shown to be quite performative, and to our knowledge, this is the first time that we use mass diffusion has been used for this inverse design of thin films. It shows a relatively good performance compared to nearest neighbor retrieval of the training data, and also to competitor model, which is autoregressive OptoGPT. And it has also been shown, I will show this later, that it's possible to discover physical design motifs from its own, without specifically training on that. The architecture, it's using a transformer architecture. It's conditioned on the spectra with cross attention, and has this, with the self-attention, uses the embedding of the stacks of the sequence. And it also uses the time step, of course. And in the end, it's projecting towards our vocabulary for each position of the sequence. When we do some aggregated performance comparisons, here you see 3,000 points, testing points, and here we compare OptoLlama against OptoGPT, and also the nearest neighbor lookup. So if one of those points is below this dashed bisectional line, then it means the performance of the model is better than the nearest neighbor in the dataset. And if it's above it, it's worse. And as you can see, most of the points for OptoLlama lie below this line. And this is also, you can also see this in the aggregated mean absolute error on the spectras with these values here in this box here below. When we now open these aggregated results towards the diffusion steps, so in each diffusion steps you calculate this metric, and then you can get this plot. And in the first, let's say, 400 diffusion steps, the performance of the model is relatively bad. But it converges down, and at around diffusion step 400, it surpasses both baselines, and the last diffusion step, it converges to 0.014 mean absolute error. And this shows that this type of architecture is able to correct on its initial predictions during the diffusion process. Then I want to also show one example, which is an out-of-distribution example. In the archive paper we have a couple more, but like this one is, I think, the most illustrative. Here we have a sort of target which a material scientist would be interested in. Let's say you have a certain reflectance peak in an area. Here it's 550 nanometers of a certain width, and about the other region you have either like just like these 1 or 0 values, or like you're not so much interested in that. So for this example, the nearest neighbor actually is a no stack. So like just a completely free stack with no interference. And when we now prompt OptoLlama with this target, we get a stack which actually represents our characteristical feature which we want to preserve, which the nearest neighbor completely misses, and still can improve on that with the mean absolute error a tiny bit. So the model is able to still address the characteristics, even though like the nearest neighbor in the training data is completely missing that. But when we now look not at the spectra, but of the stack of this, which created the spectra from the model, we can see something very interesting. And what you see here is this oscillating block curve. And this is a mixed, like when you take the stack and you look along the height dimension, you see this alternating high-low pattern, high-low refractive index pattern. And this is actually a known sort of motif in material science. It's like a distributed Bragg reflector. And yeah, the model recovered this completely on its own, because when we look at the occurrence of these type of structures in our training data, we can see that it has a low, here, doesn't work. Anyways, it's like the first pillar, it has a low frequency. This is everything counts, which is 3 layers of high-low index material alternation. And in the examples we look at, this frequency of these type of structures is much higher, and also longer sequences can be found. Yeah. So this brings me to my conclusion. OptoLlama is the first time to use mask sequence diffusion on thin film inverse design. It's performing quite well against the nearest neighbor, and also against an autoregressive OptoGPT. It can recover some physical motifs, and for an outlook we want to scale up the dimensions, and also make the simulations a bit more realistic, because they're relatively simple at the moment. Okay, then a quick head up, we have an open PhD position at HZB and ZIP from Hybrid Grad School, and thank you for your attention.
Yeah, thanks a lot, Jonas, for the talk. Any questions from the audience? There's one.
Hi, Jonas. Thanks for the talk. So I don't know if I get your idea right here, but if I understood correctly, what you are given, what you want to predict here in the end is you give the stack of the thin film, and then you can predict the spectra. Is that correct?
No, I want to do the other way around. So I give it a spectrum, okay, and then the model gives me like a stack.
A stack, okay.
And I can simulate the stack again in the end to compare it to my target.
I see.
Yeah.
So in that case, which is the inference time that you have in this scenario?
We do multiple draws to get like a bunch of samples, but like if you do like 10 draws, this is on your local hardware like 20-30 seconds or so.
All right. Okay. Thanks. Yeah.
And there's one question here from Carsten.
Thank you. I really like the idea. It's really cool. I was wondering if you went so far then to go to predict a sequence and then really build it and see if what you predict is really turning out as the correct measurable spectrum that you get, right? I mean, at the end you want to, I guess, propose a thin layer setup, right, and then see if what you predict is really what you can measure, right?
Yeah.
Do you go to that?
Yeah.
Do you go that far?
So far, no. We have like closed loop with a physical simulator. I mean, the simulator itself is relatively known and also validated itself. But like we didn't, like this is an interesting direction to go after. Like OptoLlama is to make the simulations more like noisy, to also encompass some like fabrication errors, like thickness drift or like angle variance and stuff like this. So currently the simulator is proven or like checked against, but like some redundancy would be interesting to incorporate into the model.
All right, let's thank Jonas again. Yeah, and now I'm really